Hello everybody, and welcome to a new video. This video is largely experimental. I'm just going to be trying out some new settings on my camera, some new equipment, some new techniques, and just generally trying out some new stuff. One thing we'll be messing around with today will be this 1000X USB microscope. We'll be having a look at this LED USB flashlight thing and trying some new settings on the camera. If you hear kind of a repetitive clicking in the background, that's the autofocus, because I actually have it set now to continually focus instead of just focus on one point, because I was being really bad about making sure I was staying in focus. So if the clicking noise is too annoying, I'll stop using that in future videos. Anyway, so this is the I showed these briefly in a previous postbag video. It's just a LED light bar that you plug into a USB port, and you get a really nice bright wash of light there. They're cold white, which I'd prefer if they were warm white, but I think they were less than $1 each, so you can't really complain. Anyway, so let's just pop off the end here and then open it up. And what we'll see here on the inside is 8 LEDs. A couple of resistors, and the USB port. Not much for it, but go ahead and slap it underneath the microscope here. So just going to go right ahead and get that started. So I'll just slide it up under the microscope here. There should be a image right about here now that will be showing you what I'm seeing in the microscope here. So we'll just get this to focus down. Let's back it up just a little bit here and focus it down again. There we go. Focus on it is a little fiddly. Surprisingly sharp image for something that cost, I think it was like $6 or something. Anyway, so here we go. To give you an idea of the scale of what we're doing here, I'm going to be pointing at it with the lead of this 0.7mm pencil that I've filed down to a sharp point by rubbing it on a piece of paper. Anyway, so we've got the positive lead right here, and that's coming into a track that we can see right here. I hate these shiny tracks, but it comes along and it actually goes all down one side of the LEDs. That means these LEDs are in parallel. And then we get to the other end, and we'll see the other track on the other side of the LEDs coming down the other side here, and then it comes, I'm trying to glint the light off of the track because it makes it easier to see. We'll see that comes down and around here into this 3R3, which is a 3.3 ohm resistor. And then that, 3.3 ohm resistor, and then that comes over here into the other end of a 3.3 ohm resistor, and then that track comes out and over here and over to the negative lead of the USB. Interestingly enough, there's an absence of a resistor across the data lines, which if you plugged it into a computer or a power bank would, well, I guess power banks don't really care. They probably provide full current no matter what's plugged into them. But if you plug this into a data port, if you have a 30 ohm resistor across these leads, it will indicate to that data port to provide power only, and it will actually increase the amount of current that you can draw out of that port. So yeah, that's pretty cool there. Now, a neat thing about this microscope, let's twiddle the focus just a little bit more here. There we go. Oop, went too far. It's not the... It's a little flimsy, so you have to kind of be gentle with it when you're adjusting focus and stuff. There we go. Anyway, so you can just see the bond wire coming down here to the LED chip, which is just that tiny little black spot in the center, and then you can... Oh, it's falling out of focus again. There we go. And then you can just see the other bond wire right there. So that's kind of cool. I've never actually gotten to see that up close. Maybe at some point, if I'm feeling up to sacrificing one of these devices, I'll scrape the phosphor gel off of it, and we'll have a better look at the inside of an LED. Anyway, so that's enough with the close-up look of the LED. Let's go ahead and take some current measurements and whip out a quick schematic, and that'll be that. Anyway, so it's a super simple circuit. We have the positive lead here coming across, and what did I say, 8 LEDs? 1, 2, 3, 4, 5, 6, 7, and 8. I won't draw all of the lightning bolts anyway, so those come out like so. And then we'll come down here, and then I didn't leave really enough room for this, but then we've got, well, I'll just branch it off like this. We've got 2 resistors like so, and then to the negative. And these resistors, I believe 3R3 should be 3.3 ohms. 0.3 ohms. Right, so that's that. Now, if these are 3.3 ohms, let's take a quick measurement and make sure that they're actually 3.3 ohms. So we'll set my thing to resistance there, and we'll go ahead and go across one of these resistors. Come on. .6 ohms. Oh, you can't even see that, so let's move this so that you can actually see the display and measure that one more time. So there we go, 3.5-ish ohms. So let's move that out of the way. If we know we've got 2 3.3 ohm resistors in series, that means we've got a total of 6.6 ohms. We know that the forward voltage of these white LEDs is about 3 volts. And we know that here we've got plus 5 volts. So we can calculate the current that we're going to see in these LEDs with this information. So we've got 5 volts coming in. We've got 3 volts being dropped across the LEDs, which means that we've got left 2 volts across the resistors. Now, our good old Ohm's law, V equals IR. Well, we know V and we know R. We want to know what I is. So we can move I to one side of the equation by doing a little algebra. We divide both sides by R, and we get I equals V over R. So let's grab a calculator real quick and find out what that is. So our voltage across these resistors, because that's the important part, we're calculating the current going across these resistors. The voltage being dropped across those resistors is 2 volts. Well, technically it's 1 volt per resistor, but I'm combining the 2 of them. So we've got 2 volts over 6.6 ohms equals 2 divided by 6.6 equals 0.3 amps, or 300 milliamps. And then, of course, that means that's 150 milliamps per resistor. And being as we know there's 1 volt per resistor, we multiply that by 1, and we get 150 milliwatts. 50 milliwatts per resistor, which is well within the rating of those resistors. I think these are 250 milliwatt resistors. So they're rated well within the tolerance of the resistors, and there's 2 of them, so it'll spread the dissipation out, and they're on an aluminum-backed PCB with this piece of aluminum extrusion, so there's plenty of heat dissipation. It's really a very well-built piece of gear. So, just for fun, let's see, here's my USB ammeter. Well, here's one of them. So, let's go ahead and plug this into there, and we'll reset it. And then we'll plug in the lights here. And look at that, it's reading 0.29 amps, which we calculated that it was going to be 300 milliamps, and it's reading 290 milliamps. So it's always pretty cool to see those come out as you calculated it on paper. So that's all for today. If you enjoyed, go ahead and click that like button and or start a comment or start a discussion in the comments below. If you haven't already, consider clicking about here to subscribe to my channel. Right over here, where the microscope was, will be a video that YouTube thinks you'll enjoy based on your watching habits. Right over here will be some playlist of some sort. I don't know what this was. I guess sort of a product review kind of thing? Teardown? I guess I'll have to start a teardown playlist. Anyway, right here will be a link to my Patreon, which you can use to help support further videos like this one. Thanks so much for joining me, and we'll see you next time. Bye-bye.